We know the composition of asteroids that have been observed and studied for decades. Most asteroids fall into the following three categories: C-type, S-type, and M-type. C-type, or carbonaceous asteroids, also known as chondrite asteroids, are the most common. Their composition is believed to be similar to that of the Sun, although they lack hydrogen, helium, and other volatile compounds. They are dark in appearance, and they are among the most ancient objects in the solar system. S-types, or stony asteroids, are made up of silicate materials and nickel iron. They account for approximately 17% of all asteroids, and they are the second most common.
One is one we call S-type. These are often ones that were referred to as more stony type objects, and we think are very similar to a type of meteorite that's very common that lands on the Earth called ordinary chondrites.
M-type asteroids are metallic and much brighter than C-type asteroids. They are made of nickel, iron, iridium, platinum, gold, or other precious metals, either pure or mixed with different amounts of stone.
M-type asteroids are very unusual. Some of them may actually be metal. They may actually be produced in the interiors of asteroids. The core material has managed to escape the asteroid, probably in some gigantic collision. Other M-types, though, may be different compositions altogether, and there's still a great uncertainty about exactly what all of the M-type asteroids are.
If we want to study the composition of an asteroid, one of the best ways to do so is to analyze meteorites at an automated mineralogy lab, since many of them come from asteroids. The team at the Mineralogy Lab of the Geology and Geological Engineering Department at the Colorado School of Mines can examine the compounds of any meteorite sample with extreme precision.
All meteorites are fragments of rocky or metallic matter that's been transported from objects out in the solar system, and they've landed on the Earth's surface. And we can collect them and study them in the laboratory and work out their chemical composition, which minerals they contain, and therefore we can extrapolate the resource potential of particular bodies that exist elsewhere in the solar system.
Our automated mineralogy system is SEM-based, so we're using a scanning electron microscope to basically scan our sample. We have to prepare the sample. It is really important that our samples have a perfectly flat surface. So we have to polish our samples down to 1 micron. So the surface is perfectly even, so when we have the beam interact with the sample, we don't have other interaction features that will change the result of our interaction. We have our electron beam interact with the sample, and then we investigate basically the interaction product we get from the beam interacting with the sample. The result from this interaction we compare with the lookup table, where we have definitions for all minerals and phases that are of interest to us. And then our software program, the automated mineralogy software, will produce a false color map based on the definitions written and based on how it compares the analytical data with our lookup table.
Therefore, we can determine if the sample has more or less iron, nickel, platinum, or more or less of any other mineral. All asteroids, no matter their composition, are rocky remnants left over from the early formation of our solar system about 4.6 billion years ago. So they offer us clues to unveil the most hidden secrets of our most remote past. We've been exploring and studying asteroids for decades to understand what happened before us, before life on Earth, and even before Earth itself. Asteroids, considered floating fossils, can help us trace the solar system's evolution from a primordial disk of dust and grains. Asteroids can help us understand how the planets were formed, and the origin of life on Earth, since there are theories that claim that the massive impact of asteroids was mainly responsible for delivering elements of life to primitive Earth.